planet in here. So for Pluto, our orbital radius, and this is average orbital radius, by the way. So it's 5.91 times 10 to the 12th cubed divided by the orbital period, 247.9. Oh, they give it to us in years. So years times 365.25 days per year. And all that squared. How dare they change units on us? But I guess it explains why they didn't put units in the header. I think it's gonna be somewhere around 1,124,000, but
for the bottom, if those two numbers times each other, then squared, right?
yes.
Okay, so I got 720.86.
720.86.
Yeah.
Wow. We just showed every physics textbook wrong?
Oh, I forgot to cube the top, sorry.
Based on a lot of lab results I've seen over the years, there are days I'm wondering, how does anyone believe anything in the textbook?
Okay, that time I got 2.51 e to the 30th.
Yeah, that can't be right.
Okay, well, I got close to that, 2.5178. Yeah, that's
Times
what
10 to the 30th,
28.
2.5.
2.51784447 times 10 to the 28.
All right,
That exact same number, but times 10 to the 30th. I just didn't say all the decimals.
which makes me think this number's wrong.
So,
Did I write a number down wrong? So that's 247.9 times 365.25 would be the number of days of the orbit. The orbital radius, 5.91 times 10 to the 12th, that's written down correctly. Over here, the radius of the Earth's orbit, 1.5 times 10 to the 11th is right, and that's the right period there.
for the one over there, I got, 2.52984158 times 10 to the 28.
All right,
Which one's right? I got the one over there,
Yeah, I got the one over there with the 28.
the 28, the 2.5.
did you get this one over here?
No, I got
I got that one.
You got this upper one.
the one
Well, those two numbers should come out to about the same, so that's why I'm having more faith in this one right now, but
I just got the 2.5178 and
yeah,
times
that's,
10 to the 28.
okay.
that's what I got.
So you got this over here?
No, I got
You
that.
got
number,
the- so
2.5.
There seems to be general agreement over there on that one.
Yeah.
Yeah.
But this one over here, people are having issues with.
I just times the bottom numbers first, and then I did the 5.91 12 to the third divided by that number that I got, the timesing the bottom, which is like that, and I just squared
Yeah,
it.
I'm thinking this number can't be right, this 1 million.
And then I just squared it.
Is that e to the 28 or e to the 26?
That's a 28, oh, over here,
Oh wait, I just got that number.
you got this number
Yeah, I
now?
got that number too.
Okay.
What'd you do different?
I have no idea.
I don't know, this is the only time I did it.
It's magic.
Yeah.
If in doubt. Okay, so we get pretty much, yeah, it is pretty much the same number. This ends up rounding off 2.53 versus 2.52. Pretty darn close. Now, here's the historical significance. Kepler was looking at incredibly precise astronomical data. Now think about what the movement of the planets is from where we are. We can see, because we're going around the sun, and we have another planet going around the sun, but we're traveling at different speeds, and so what you might see a distant planet, and basically it looks like it's going to the left each night at the same time, and then it starts moving off to the right as, you know, it's sort of ahead of us, and then we pass it, and then it looks like it's going the other direction. I think in astrology it's called retrograde. I could be completely wrong on that. He was able, over 40 years of looking at incredibly precise information, was able to piece together the fact that if you take the orbital radius cubed divided by how long it takes to go around the sun squared, you get the same number for every planet in the solar system. He had no idea why, but he noticed that pattern. He noticed two other things over the 40 years of studying this stuff. He noticed that planets actually don't travel in circles. Now, we did an approximation here with enough patience and calculus background. You can actually look through the full derivation, but the circular approximation works pretty darn well, especially since we came up with the same result that Kepler did. An ellipse, if I take 2 points. So imagine I've got a cork board here and I have 2 pins stuck in it. And I have a string sort of dangling between the two. I take a pencil or pen and I pull on it so that it's stretched. And then I start moving around. So this from here to the pencil is one length, from here to that is one length. In other words, the length of the string is constant. So from here to here to here is the same no matter where I am. So if I trace that around, that actually is an ellipse. Very badly drawn here, but it's an ellipse. This point right here, or these points, are known as foci, or a single one is known as a focus. So Kepler noticed that planets travel in an ellipse with the sun at one of the focuses, at one of the foci. And the third thing he noticed, since things are traveling in an ellipse, so I have my sun here, I have planet here, zipping around. Now the orbits are really much closer to circles than I'm demonstrating right here. Pluto is probably the most eccentric, most elliptical, which is why I chose Pluto as the example there. And I'm going to try to draw that better. Let's see, what do I need? I need that. So sun, planet, zipping around. Now the gravitational pull is towards the sun. Notice that because it's not a circular orbit, part of this pull is in the direction of movement, and part of it is perpendicular to it. The part that's perpendicular, that's the centripetal part. That's the part that's getting us to curve. The part that's in front, right here, is actually at this point in this orbit, is causing the planet to speed up. So the planet speeds up, goes zipping around the sun, then slows down, gets to this point, then starts speeding up again, slows down. Once it gets past this point, so it's slowing down in this direction, slowing, and speeding up. Speeding up, slowing down. So since the Earth is not traveling the same speed, he did notice that, take any time period. So let's say in a month that the planet moves from here to here. This area right here that is known as, it's the area that the planet sweeps out. So from the planet here, so this is 1 month. Here, when it's traveling faster, it's going to go a farther distance along here. if that's 1 month, this area here and this area here are the same. Planet sweeps out equal areas in equal time. And what he did was absolutely amazing. However, Kepler did not have a clue about why any of this was true. Newton comes along, Newton can explain it. The full derivation is more sophisticated than what we've done right here, but the gist of it still holds. We still get to the same place. This is an average radius, and this is still the period. This law right here, the equal area, equal time, is actually conservation of angular momentum. If you're swinging something around your head, if you put your fingers up so it starts wrapping around your fingers, that thing's gonna get faster as it gets closer to the axis. So as R gets smaller, the speed gets bigger. Similar to, as the moment of inertia decreases, the angular speed increases. The elliptical orbit comes naturally out of just the mechanics. F equals ma. It comes straight out of that. And this right here, we derived it, that also comes out of F equals ma. So I make the claim that I'm glad Kepler was dead by the time Newton came along. Imagine you spent 40 years of your life working on the same thing. You're almost done. You're feeling really good. And you're in a bar one day and you meet Newton. You get to talking about what you're working on. Kepler goes first and says, oh, I've been working on planetary motion and trying to figure out some rules to guide it all. And Newton goes, oh, you're working on that? You got 2 afternoons, I can show you how to do it. 40 years of your life.
How long after was Newton?
I think it was about 50 years after. It might have been longer, but I did look it up and I did confirm that Kepler was dead by the time Newton came along. That would probably have been from Newton's birth as opposed to when Newton really was doing his primary work. Now, one of the reasons why Newton's laws of motion were accepted so quickly was the fact that he could derive Kepler stuff from it. However, Kepler laws of motion, yeah, most textbooks have it in there, mainly because it was an attempt historically to come up with rules. Just it fell short, but I'm not quite sure he could have really done much better. I mean, Newton had to invent calculus in order to explain his stuff. And for you Leibniz fans out there, yes, I'm sticking with it. Newton invented calculus. So before we do the break, you know what, let's do the break, and then we'll wrap things up and talk about quiz, the next quiz, next 2 quizzes actually.
The next week?
There will be a quiz next week, most likely. But we'll just take a break, stretch legs. We'll come back and bring order from the chaos.